Hello, my name is Sylvie Trudel, and I'm glad to present you today Module 7, Estimation Process in Software Engineering for Estimators. The work or content in this video is based on Dr. Alain Abran's book, Software Project Estimation, the Fundamentals for Providing High-Quality Information to Decision Makers. Before we start, we have some preliminary remarks. Well, first, software estimation can be done from different sources. Functional process measured in function points are our initial source. Next, our preferred function point measurement method is COSMIC. Now, COSMIC is an acronym which stands for Common Software Measurement International Consortium. In addition to Dr. Abran's book, the direct source for this presentation comes from a document entitled Estimation Process in Software Engineering. Let's look at an overview of productivity model and estimation. Here in the middle, we have the productivity model, which has been built from a repository of productivity data, namely past project, effort, and functional size. When we want to estimate a range of or obtain a range of estimates, we need to first estimate the inputs of our new project, inputs that are related to the software product, the software process, and some constraints, all of which should come with a level of confidence in the input. Our productivity model should also contain some level of confidence in the model, and in that case, we will really obtain not a single estimate, but a range of estimate. To obtain that, we'll cover the following 4 topics: function point measurement, estimates of input, analysis of the productivity model, and estimation result. For the first topic, function point measurement, well, what is measuring the size in function point? Well, it's to apply a function point measurement method. The ISO 19761 standard describes the activities required to measure the size of software project in cosmic function points, or CFP, which is the unit of measurement. Currently, Cosmic version 5 measurement manual can be found at cosmic-sizing.org/measurement-manual. Cosmic-sizing.org because it is a not-for-profit organization. All the documents available on the website have been done from volunteer work of collaborators throughout the world. The manual is written in several languages, including English, and currently it's also available in French, Spanish, Italian, and Chinese Mandarin. Previous versions of the manual are also available in up to 12 different languages. Let's look at estimates of input. The estimates we have, our productivity repository, have been largely inspired from a project database called ISBAG, ISBSG, which stands for International Software Benchmarking Standards Group. It is also available, not for free though, at isbag.org website, and it does contain a number of variables and projects. Not all variables and not all projects are necessarily relevant to our current estimate. This step, therefore, the estimates of input, we have to do the selection of variables, selection of project, and also analyze these inputs. When it's time to select the variables, what we need to understand is that there are 2 types of variables. The dependent variables, such as effort and duration, because those will be derived from the independent variables, such as functional size, programming language, type of development, development platform, the main programming language, etc. So there's also the quality of data that must be taken into account. So in the ISBAG database, there's quality A, B, C, or D, A or B being the best quality. And we have this level of quality for what Icebag calls unadjusted function point rating, and also the data quality rating, which is the quality of measurement and quality of efforts, typically. So in the Icebag database, one can find more than 100 variables. That's a lot, and not all these variables are relevant. So the selection of the variables depends on the purpose of the analysis. In our case, we want to produce a productivity model so we can estimate a project with similar characteristics than the one we are looking for. So we need to select project from now on. The selection of project can be based on the content of the variable. Here are some examples. The functional size. Suppose that our project, whether we have only one project or just a couple of projects, have a functional size that is between 50 function points and 400 function points. Well, we don't want to look at projects that are smaller than this or bigger than 400. So this will be important to filter out which project we need. The development type. There's new development versus enhancement. In the Icebag database, we can also find the redevelopment development type. That means you have rewritten a new software based on previous technology that is no longer supported. But in our case today, we will not be touching the redevelopment projects. There's business application project versus real-time software project. We will look at today is business application project. The main programming language, for example, the Java language only. There's the quality of measurement in function points. So A and B being the best, like A is the top quality rating, B is the second best, and there's C and D. C and D are, of course, less good measurements. And there's the quality of the effort measures as well. And also the development platform. There could be mainframe, PC, multi-platform, such as distributed systems, etc. So we've applied these values on our own project database, and we obtained a selection of 59 projects that are shown in the table right here. For our purpose of measuring the project productivity, there are two critical variables. In that case is functional size, which is the column here, and the effort, which is this other column with the blue header. The other variables that we find here is the quality of data. Here's an ID of a project. There's the application type. They are all business application. Development type, some are new developments, some are enhancement. The primary language, Java. Here is the development platform, all on PC. Then let's look at some analysis of these inputs. Well, what we have there is 23 projects of new development type and 36 projects of enhancement type. The projects are all Java on PC platform, all business application project. So because we want to minimize the variables values. So the construction of our productivity model precedes the construction of our estimation model. And productivity is really based on past data. So those 59 projects were all past projects, while the estimation model is a projection of the expected results. So the first analysis, we will look at average, minimum, maximum, median, and standard deviation. So we have here the size, which is the independent variables, and the effort, which is the dependent variables. Well, the results show a large variation between minimum and maximum for both size and effort. And the median differs also greatly from the average. And if we look at the standard deviation, it's even greater than the average in both cases. Let's look at the data graphically. This graph displays the coefficient of determination here and the linear regression of the 59 projects presented above. Now, it indicates that the coefficient of determination is 0.66, which is a little below the arbitrary criterion suggested in software engineering for productivity model, which would be 0.70. There's the slope of the line here, that is the line being AX plus B, is 12.381 for parameter A, and 68.4 typically for parameter B. That is when cosmic size is 0. So it's where the line will cross the y-axis when the size, because x is the size, y-axis is the effort. So effort equals to 12.38 times the functional size plus 68.4 typically. Now, what are the formulas in Excel? Because you only need 2 rows or 2 columns, I may say. One column for the y values, the effort, one column for the x values, the functional size, and those are y's and x's, and these are the formulas in Excel to obtain these values. Now, constant in statistics in the linear regression formula, we have put them in bold. They are optional and do not have to be filled in first. The next step would be to search for outliers. And this is done on one variable at a time and one step at a time. The fastest way to find out if there is an outlier in a sample is to use the Grubbs test. And this URL will provide a free tool where you can input up to 2,000 elements at a time for a single column. Now, applying the Grubbs test, as a result, we looked at this and said, we first started with size, and it says, yes, there is an outlier, and it's project 59, where the critical value of Z should not exceed 3.193. And for project 59 right here, the critical value of Z came out with 3.235. So therefore, this one was an outlier. We've redone the process, the Grubbs test with the effort, and it found out that project 56 was also an outlier. Now, it's up to you. If you remove the outlier and you look back at your coefficient of determination, if the difference is negligible, like less than 5%, then you could leave your project in. You can also decide to take them out. It's up to the person who does the analysis at that point. But if the outlier makes a big difference on the coefficient, then it should certainly be removed. Let's show an example with 10 different other projects, okay? Suppose this representation here of 10 projects. Like this first graph includes an extreme value, that value here. And when we looked at the R square, well, it's over 0.75. So it might suggest an acceptable productivity model for estimation purposes. But the Grubbs test shows us that this value is indeed an outlier. Then if we take it out and we make the same representation with 9 projects, well, this second graph does not include that project, and it shows that the R square is now 0.12, which is much lower. So it changes completely the interpretation of results. So the grub test that is attached here really has suggests to eliminate the project number 3 of a value of 771. Now, the grub test identifies only the largest outlier, a single one. Therefore, once it is removed, then the grub test should be run again on that single variable to identify if there is an additional outlier. Then we need to repeat the grub test until no additional outliers are found. Now, looking back at our data, we've rounded the values with 2 decimals. Y equals, Y is the effort, 12.38 times the number of function point plus 63.39. Now we want to calculate the mean magnitude of relative error. The relative error is the estimated value that was obtained for a single data in our repository minus the present value of that data. So we take the size, we estimate the value, and we subtract the actual value, and we divide by the actual or present value. That's the relative error. So it can be positive or negative. Then the magnitude of relative error is the absolute value of these. So instead of having it negative, we take the absolute values. And the mean magnitude of relative error is the sum of all these MRE divided by N, the number of projects. So we've applied those formulas on our 59 projects. And it helps us calculate the error margins. So in red, so all these, we have an average of 162% of margin of errors. The estimated effort is on the left. It's in this column here, estimated with our new formula. This is the actual effort of the project. This is the relative error that's calculated between both. The magnitude of relative error, and here's the mean. So in that case, those that are in red has an absolute margin of error of more than 300%. So there's a couple of these. In orange, like this one here, this one there, it's a margin of error between 200 and 300%. Now for the first 12 projects, there are 6 projects with an error margin greater than 300%. There are 14 projects with an error of 200% and above, so the red and oranges altogether, including 13 projects of less than 75 cosmic function points. A single project with 304 cosmic function points has a margin of error over 280%. So 5 of the first 12 projects with less than 25 cosmic function point have an error margin greater than 200. Then for that reason, we have analyzed those smallest projects of 25 cosmic function point and less. So to go further in the analysis, it seems interesting for us to carry out analysis on these small projects. Now, the relationship between size and effort for small project is quite weak. It's only 0.132. Okay. Now, if we take away those projects, so it's 11 projects. So we're left with 46 projects in our case, because we've taken out the two outliers. So 59 minus 2 is 57 minus 11, 46 remaining project. And in that case, our coefficient of determination is a little over 0.63, so almost 0.64. And looking at the biggest project, there are 6 projects over 200 cosmic function point that are here. And we ask ourselves, could we find outliers due to these 6 projects with more than 200 cosmic function points? Well, we do not believe, since for every 50 cosmic function point interval on the horizontal axis, there is at least one project. In addition, the forces are relatively well distributed on the vertical axis. Like this one is maybe an outlier due to low effort. Now, if we want to estimate the result, if we want to keep the previous 46 project, there is one possible way to present the results of the estimate. Now, we know that the effort equals A times functional size plus B, in that case, 12.24 times number of function point plus 95.284 hours. That was on the previous graph. So A being 12.24 and B 95.284. So if our new project is of a functional size equal to 74 function point or cosmic function point, then the effort will be 1001 hours. Let's round this up to 1000 hours. Then our result table, using 74 function point and a desired arbitrary error margin of 20%, let's say, okay, we obtain the following table. So the equation, the effort based on the equation is 1000 person hours. So 20% less is 800, 20% more is 1200. So our interval is between 800 and 1200 hours. And this is what this table shows, that the minimum effort would be 800 hours and the maximum effort is 1200 hours, with 1000 hours for the estimate of the equation after rounding off the results. Of course, that estimate is only effort, is not cost. To estimate the cost, you'll have to derive the cost based on the how much a person hour cost in your organization. Now, many organizations have a standardized hourly cost that may work for any staff available, and you have to also estimate the risks, because the database, the effort that's included in the database does contain a certain level of risk mitigation. Now, is your new project, that the one you're estimating, has a similar level of risk, or much lower level of risk, or a higher level of risk? Then this will decide what's the contingency you should put. In our example here, the 20% was an arbitrary error margin. However, in your typical project, or the project you want to estimate, it is possible that this error margin needs to be bigger or could be also smaller. In conclusion, it is possible to have an estimate of software engineering project using an estimation process. And to this end, it is necessary to have a project database with a number of variables characterizing each project, because you cannot estimate a project for which most of its characteristics are very different from the project database you have. So you need to compare apples with apples. We need to select and analyze projects to determine the productivity model based on these characteristics, analyze the productivity model so we can eliminate outliers and make sure that the data is of quality, and apply the resulting productivity model to the project that has been measured in function point to obtain the estimation results. And make sure you do not present a single result, even though managers, they're asking for a single result, but it is not a good practice. The good practice is that you ideally present an error margin. That means a minimum and a maximum. And if the project is risky and the manager only wants a single value, then you provide the maximum, just in case. For further information on estimation and on the COSMIC method, please feel free to access the COSMIC website at www.cosmic-sizing.org. Thank you.